All right. Good evening, everyone. So, I think I'm audible. So, okay. So,
Yes,
thank you, Satish. So, um, I think we have around 11 people here. So, maybe we'll get started. More people will join soon. Uh, so, First of all, thanks for enrolling to this course and also joining this, doubt clearing sessions. And uh, Myself, I'm Ganesh Kumar. I'm a PhD student at IIT Gandhinagar. So my areas of interest include aircraft and rocket propulsion and also computational fluid dynamics. So my research is, mainly involves rocket propulsion. Uh, I try to predict performance of solid rocket motors using CFD techniques. So that is my research, but my areas of interest also includes aircraft propulsion. So uh, I requested Professor Chetan Mistry to be, a tutor for this course, so that, uh, and also I thank Professor Chetan Mistry for allowing me to be the tutor for this course. So that is about me. And I also welcome you all for this Aeroengine gas turbine cycles course, and also to this session. This is, particularly important, course, I would say, because even as a developing nation, uh, we need especially a lot of engineers, especially in this field. For example, the gas turbine engine design field, and uh, you must have already noted after going through first a few weeks of lectures and also welcome email from Professor Chetan Mistry that it's a this course actually prepares you for a bigger, uh, you know uh, field of study, which actually directly contributes to nation security, defense, for example, and it keeps on going. So it is like a starter or introductory level course, which is going to involve a lot of advanced concepts uh, uh, to get you started in this, especially focused research field. Okay, and uh, uh, and this particular session is going to be interactive, and I will be, uh, it will be for a 2 hour session. It will be a 2 hour session, and I will be solving few questions. Probably that will not take much time. I will be solving maybe maximum like 30 minutes or so, and uh, what I would leave the remaining 1 hour or 1.5 hours for you to ask questions. So this is supposed to be an interactive session. So please feel free to switch on your mic and videos, and if you have any doubts in between, you can just stop me anytime and you can ask, or also you can stay back after I solve the questions, and then you can ask your question. Okay. Uh, this session is particularly for you as a learner. Um, uh, if you since it's a advanced level course, I think you will have a lot of doubts while going through the course, uh, and especially for you, if you have any doubts, you can you know, come to this session, and you can ask your doubts. Okay, and this is going to be a weekly session until the end of this semester, end of this course, for 12 weeks. And we may also have one more session just to revise what are all the concepts that we uh, covered in this course. Occasionally, we may also expect Professor Chetan Mistry to join, so that you will get an opportunity to interact with him. Okay. Uh, uh, yeah. So, on that positive note, I welcome you all to this session and also to the course. Uh, Before we start this session, do you have any doubts? Do you have any, uh, uh, if you want to ask any uh, thing, you can ask about the operation of this doubt clearing session. Uh, so, in the meantime, let me quickly check whether the recording is available. Yeah. So, and also one more thing I forgot to mention, this whole session will be recorded, the whole entire 2 hour session, and I will upload it in the YouTube video, and also, I mean, I upload it in the YouTube, and also uh, the problems we solve during this session will also be uploaded in a Google Drive, and you will be given access. Okay, so that you no need to worry about. But I actually strongly encourage you to attend this session, so that you will get an opportunity to clear your doubts then and there, right? Okay. um, and yeah, so I'm going to repeat the same thing. It's a interactive course, and I especially encourage you all to ask doubts or stop me anywhere in between. Uh, yeah, make it more interactive rather than a one-way conversation. Okay. All right. I hope my screen is visible. So, all right. I assume that there are no doubts till now. Anyway, we will. Today, what is the agenda is, I have one question in here, so I will be solving that. In fact, you are going to help me solving that. Basically, that is how I do it. So this one question we will solve together, and then we will try to identify some interesting physical insights out of this problem. Uh, and that is going to be primarily focused on this week's lecture contents, and also it is going to help you in solving the assignment problems. Okay, and I actually had a look at your assignments. I think it's a fairly if you go through all the this week's content, it should be fairly easy to solve these problems. So uh, anyway, you can ask me doubts. Okay, so with that quick note, let's just quickly uh, rethink what we studied. I hope everyone gone through the week one content. So what we really studied in this course is, or really studied in this week one content is, we introduced something called gas turbine engines, and of course probably everyone must have known gas turbine engines even before attending this course, but still we introduce the gas turbine engines, and the important performance parameters we introduce. Example, so we introduced thrust, for example. How do you calculate thrust for any gas turbine engine? And also there are multiple efficiencies we studied: thermal efficiency, propulsive efficiency, overall efficiency, and also propeller efficiency for turbo shaft engines. So multiple efficiencies we studied, and also another important thing is specific fuel consumptions, how to calculate them, and what are the implications which comes with specific fuel consumption. Is all these things we studied. In addition, we also studied this aircraft range and endurance factor, right? So I hope everyone have gone through this week one contents. So in that way, so I'm just going to quickly recap uh, certain important things that we should uh, take forward for this course. So from week one, okay. So this is the diagram over here is a typically simpler gas turbine engine. Okay. Uh, Probably my diagram might be very bad, but you can say like some of the important uh, devices are there. So for example, we have the inlet over here, and then you have compressor. Then compressor is coupled with a turbine over here. In between compressor and turbine, you have a combustion chamber, something called combustion chamber, and then you have a nozzle through which airflow enters. So airflow enters through the inlet, and it goes through all these components, and then it exits. Okay, so this is how. So the entire working principle is, we are doing something to this airflow so that we will end up having thrust. So that is the entire concept of this gas turbine engine. And uh, so since we are interested in thrust for this engine, how do we calculate thrust? So it is a simple, so for example, if you consider this as your control volume, and if you just balance the forces, for example, you should just apply Newton's second law of motion. So if you just apply Newton's second law of motion for this entire engine, it's simple. So you consider this as your control volume, and you see that flow is entering over here, okay, and the flow is leaving, and you see that momentum entering would be m dot into v infinity, and the momentum leaving would be m dot into v net. So that is what you will see here, m dot r into v9 minus v infinity. In addition, you have 1 plus f factor, because in the combustion chamber we are going to add fuel. So the total amount of air leaving the engine is going to be the air entering plus some amount of fuel that we add. So that goes out as a that also goes. So m dot infinity into 1 plus f times the v9 minus v infinity is the momentum thrust you have. In addition, what also you have is pressure. So there is always pressure acting, right, on the entirety of the engine. For example, you also see pressure over here, okay, but ideally what happens is the pressure top and bottom gets cancelled out each other, so we don't really worry about it. And also we are interested in thrust in along this direction, right? So the pressure forces acting perpendicular to it is not going to affect anything along this direction. So we are doing a momentum balance along the axial direction. So for that we take care of this pressure forces. So if you see, the pressure force acting over here is P infinity times A infinity, and the pressure force acting here is actually P9 times A9, plus the remaining area is acted by infinity, P infinity, right? And when you subtract these two components, you will end up having this term, additional term. So you can call this as a momentum thrust, you can call this as a pressure thrust, uh, or you can say that this both contributes to the thrust of the engine. I hope everyone understand this concept. How did we derive the thrust of an engine? Okay. So if you have doubts, you can stop me anytime. So please feel free to stop. Okay. And then what we have is we have certain efficiencies: propulsive efficiency, thermal efficiency, overall efficiency. I hope everyone know about this. I just want to quickly recap. So propulsive efficiency is nothing but the aircraft power, right? So aircraft power divided by the net power output of the engine. And there are different ways of doing this. We will touch upon this while solving the problem, and we will see which is better way. Okay. And also we have thermal efficiency, which is nothing but net power output of the engine divided by the energy, thermal energy we are uh, giving to the engine in terms of fuel. So when we add fuel, it comes with some energy. That fuel is what is uh, that fuel is kind of like a chemical energy which is getting converted to a thermal energy, and that thermal energy is what increasing the temperature of your airflow, and which is going out. Okay. So here MMR is asking, is the thrust calculated in rest or motion? So this is actually a engine is in rest, okay, and then airflow is going in and out. That's it is you can call it's a thrust calculated for an engine relative to an engine. That is how you can call. Okay. Uh, and uh, Tati Pali Satish, do you have a question? You can ask. Can you?
Yes, sir. So we are calculating these velocities with respect to aircraft speed, right?
Yeah, so especially for this case, if you see, I am placing my frame of reference on the engine. So I am sitting on the engine and I'm seeing. So forces,
Okay.
the flow is coming in and the flow is going out, right?
Okay.
But when the when the aircraft is flying, the
Yes, sir.
aircraft is moving. So air is stationary. So
Okay.
as an observer, if you stand on the ground and see, it's like air is stationary and aircraft is moving with V infinity. So here, as observer, I am sitting in the on the engine and I am seeing how things are moving. Okay.
Okay. So in somewhere, in some places, V infinity instead of V infinity, they are using aircraft speed. Is that correct?
Yeah. So uh, V infinity or V naught, we say. So V naught is the aircraft speed. So uh, if you sit on the aircraft, your aircraft is moving at V naught, right? So when your aircraft is
Yes.
moving at V naught, if you sit on the aircraft, you will not know that you are moving at V naught. Instead, you will feel the air which is hitting on you, right?
Okay.
And what would be the velocity that would be hitting on you? It will be V naught, right?
Big one.
Since you are
Yes, sir.
moving at V naught, it will also come towards you with the same velocity. So that's why people usually they take the air inflow to be same as the flight speed condition.
So the conclusion is the inflow air or the aircraft will be equal aircraft
Correct,
speed.
correct, correct.
Yes.
So it's just the frame of reference change. Okay.
Okay.
So frame
Okay.
of reference you can change.
Yes, sir. Thank you, sir.
Alright. I think MMR is your doubt is also clear. Okay, I hope this doubt is also clear. Okay, thank you. Yeah, so that is about propulsive efficiency and thermal efficiency. Overall efficiency, we all know, we just need to multiply these two. And also, you can think about it as a overall efficiency. So it's nothing but the aircraft power, the power aircraft obtained, and also the power given by the thermal energy released by the fuel that you added. Okay, so that is basically uh, what determines the overall efficiency. And then we finally have TSFC, thrust specific fuel consumption, which is nothing but mass flow rate of fuel per unit thrust. So it's thrust specific, which means per unit thrust. Okay, so these are the important parameters which we will be keep on revisiting again and again for this entire course. So it's important that you understand these parameters. Okay. So uh, so assuming that there are no more questions related to this parameter, let me just quickly go through this problem I have here. So the problem here I have as a an aircraft engine consumes 100 kilograms per second of air. Okay, and the fuel to air ratio is for 0.02. So this is the amount of fuel I'm adding, and it flies at 250 meters per second. So the aircraft is flying at 250 meters per second. So at an altitude of 15 kilometer, whose ambient pressure and temperatures are given. Okay, calculate the net thrust, propulsive efficiency, thermal efficiency, overall efficiency, and TSFC. Basically, all the parameters that we just discussed for different cases. Okay, so we have uh, jet speed, which is coming out of the engine. So exit velocity of the air, which is coming out of the engine, as 250 meters per second, and the exit pressure to be 12 kilopascal. And what we did is we increased the jet speed to 350 and then kept the same pressure. And they were asking how these parameters is going to change when we change the jet velocity and the pressure. So that's the basically the concept. We have four cases. What I will do is I will solve only case one and two because others are repetitive. So you can take your time and you can solve it. And the part two of this question is uh, plot the variation of these parameters for jet pressures, for different jet pressures. Okay, that is the part two, which also I will leave it to you to explore. But we will just plot the variation at least for case one and two that we have here, so that I will give you an idea how it is. Okay, so this is the question we are going to solve. Okay, so let me just quickly write uh, given. So while I you know write down the given data of the question. Uh, so you guys let me know how to solve this question, or if you have any doubts, you can ask. So basically we have m dot of air, which is entering the engine as 100 kilograms per second, and the fuel to air ratio, which is nothing but we call it F, which is nothing but m dot fuel by m dot air, which is equal to 0.02, is also given. And the aircraft flies at 250 meters per second. So we can either call it V naught or V infinity, 250 meters per second. Okay, and then we say it's flying at the altitude of 15 kilometer. But from this data we are interested in only obtaining the ambient pressure and temperature at that altitude. Okay, so the P infinity and T infinity is going to be 12 kilopascals and 216.66 Kelvin. Okay, and so for case 1, let's write for case 1, the jet velocity UE, or actually we might even call U9. You will soon understand why we call U9. So which is nothing but 250 meters per second, and exit pressure PE or P9 is nothing but 12 kilopascals. So what we need to find out is we need to find out thrust and all the efficiencies and TSFC. So first let's try to find out thrust. How do we find out thrust? So I hope the question is clear. So uh, I don't see any questions in the chat. So I hope the question is clear and you guys also don't have any doubts. So first we need to find the thrust, and we know the thrust equation, which is nothing but m dot r into 1 plus f v9 minus v infinity plus a9 into p9 minus v infinity. Right? Is this right? So this is our thrust equation. This is what and what we have is we have all the uh, things given, which is already given. M dot r is given, f is given, v9 v infinity is given, p9 and p infinity is also given. Only thing is a9 is not given, but ideally for this case we don't need a9 at all, right? Because p9 is equal to p infinity if you look at it. So P infinity is 12 kilopascal and P9 is also 12 kilopascal. Ideally, this term automatically goes to zero. So and yeah, Satish is very fast. He already gave the solution for this. Thank you, Satish. So if I substitute this things for the sake of completion, I'm just writing all the values here. It would be 250 minus 250 plus A9 into 12 kilopascal. So whenever you write in pressure, so please make sure you convert it into pascals. Some people, some of the students, I see them, forget to convert this to pascals, which leads to wrong results. So this part automatically goes to zero. So this turns out to be, so as Satish said, it is 3187 meters. Is this right? So it's a
Velocity square, right?
why it should be velocity square? So
Okay, yeah, yeah. It's okay,
right,
sir. It's okay.
uh,
Go ahead.
see it's
Go
a
ahead.
you can think about it like this. So this is the force equation, right? So force equation requires
Yes,
the change in momentum. So
yes.
momentum is m into v. It's not m into v square.
Okay, sir. Yeah, yeah,
So
sir.
so if you change that, probably how much would you get? So probably something like 500 newtons I'm getting. So please check.
Is that 500 only?
Okay, thank you. Okay, much. All right. So this is the thrust we are getting for K zone. Okay, and yeah, you can see that our vehicle is also moving at 250 meters per second, and also the air is also, I mean, the air leaving the engine is also 250 meters per second. Still, we were able to generate a minimal less thrust. And let's look at the efficiencies. For example, let me first try to find the propulsive efficiency. So there are different formulas that we studied, right? One is T by T V infinity divided by T infinity plus m dot exit by 2 into V9 minus V infinity square, right? This is the equation that we have. This is one. The other one is, you can also write, let me call this 1 and then let me call this 2. Other thing, you can also write this as T infinity divided by uh, m dot. So it's the kinetic energy difference from inlet to outlet. So how would you write? So it would be, you can write it like this or you can write it separately also. M dot R into 1 plus F V9 square minus V infinity square. Okay. So basically this part is the kinetic energy leaving the engine, and this part is the kinetic energy entering the engine. Okay. And there is a subtle difference between these two formulas. Can you guys guess what would be the physical reason why we have these two formulas? Do you want to take a guess? How did we arrive at two formulas for this efficiency? Then both are called as propulsive efficiency, but
Sir, maybe one when the engine is on, and the second one is when it is in cruise condition, when the aircraft is at cruise condition.
um, you were close. But actually, in both the cases, actually engine is on. So think in terms of this part. So you're thinking in the right direction, but you think in terms of this part. So here we have V9 minus V infinity square, but here we have V9 square minus V infinity square. So does that ring a bell to anyone of you? So again, actually this is related to the question that both Imam R and Satish asked previously. Uh, the V naught. It's basically where your reference frame is. If your reference frame is in the engine, if you're sitting on the engine, and if you see what is the kinetic energy change of the air coming in and going out, so how would it be? So air coming in would be m dot into V infinity square by 2. So I think I missed a square over here. Sorry, off here, right? So the uh, so let's say you are sitting in an aircraft. So let me quickly draw that. So sorry, my aircraft is very bad. Okay, let's say you are sitting in an aircraft and the aircraft is moving at V naught. Okay, you this is where your engine is posted. So you are sitting here. Okay, and you see, and the aircraft is moving at V naught. Okay, and then what do you see? You see uh, air. If you sit on the engine, you see air coming to you at V naught and going out at VE. Okay, so in this case, what is the kinetic energy difference that air experiences? It would be m dot. So let's say it enters at m dot naught and then leaves at m dot. So the kinetic energy leaving would be m dot e ve square by 2, and the kinetic energy entering would be m dot e v naught square by 2. And the difference between these two is what you are putting it here. Okay, so this is your second propulsive efficiency. Now, can you think about how would you would have got first propulsive efficiency? So, is that clear what I did here?
Yes, sir. Yes, sir.
Okay.
Yes,
Yes, sir.
sir. For the first formula, it would be for potential energy.
Potential energy is not coming in this picture, right? So, air is we are at the same location, right? So we are in the same altitude. Only if we go up and down, there is a potential energy term, as you said, will come. So think about it like this. Let's say you are in the ground, okay? So you are standing in the ground, or you can say you are. So this is a altitude of h is equal to 15 kilometers or 12 kilometers, whatever it is. You somehow constructed a big building which is 15-kilometer height, and you are standing there, okay? And you see a plane passing by, okay? Uh, Mother Nehru?
Is it before combustion and after combustion? That propulsive efficiency 1 and 2. Why? Because in 1 we added only mass of air, and second we have the fuel also.
No. So here also we have V9, which is after combustion. V infinity is before combustion, right? V9 is the exit velocity. Okay. So now,
So
yeah, Satish, go ahead.
from ground, we can see that aircraft is moving with some thrust and
Hmm.
also air leaving from it. So we will add both those things, right?
Right. So actually, when you from the ground, if you just see aircraft will be moving at V0, but the air over here you will not see moving because aircraft is moving at V0, right? So air over here will be stationary, and then you will see air coming out. What would be the velocity with which air comes out? It would be something like V9 minus V0. This is the relative. So if you sit on the engine and if you see V9 going out of the engine, or if you see that air is going out at V9, now the whole aircraft is moving at V infinity or V naught. So which means that if you go to a stationary observer and if you look at it, the air leaving would be V9 minus V. Okay. So in that case, the kinetic energy lost would be mass of exit leaving, right? The m dot e, mass flow rate leaving times V9 minus V naught square. So that's what you have here. Okay. This is basically for a stationary observer, which is standing in the ground and is looking at the aircraft, which is moving at V naught. And if you sit on the aircraft and if you look at it, this is how this efficiency comes. Is that clear? So this is one way you can explain these two propulsive efficiency. Is it clear or did I confuse you all?
Clear, sir.
Okay, no problem. Even if you still confused about it, you think about it. So it's just a change in reference which is causing all this. Okay, so this is for moving observer. This is for stationary observer. Either you stand in the ground. So why I said a building, because you should not confuse with the potential energy. So that's why I said like that. Okay. This is for a stationary observer who is not moving and seeing the aircraft from outside. This is for the moving observer who is moving with the aircraft. Okay. All right. So this is that is how we got these two equations. Uh, in if not, it's all straightforward, and that's why you also see the t times v not as additional term, because aircraft is moving. That is energy. That is one energy plus some kinetic energy is wasted. So this is the total energy of the aircraft which is moving for a stationary observer. And for a moving observer, you don't see aircraft moving. You see only mass flow rate moving towards you and mass flow rate leaving towards you. So that's why you see the change in kinetic energy of the flow. Okay, that's why you do not see t times v infinity over this denominator. So I think that's enough explanation. Think about it. Okay. So now, for the sake of completion, we will try to uh, you know substitute the values here and try to find out what is the efficiency. So the thrust is, we found out to be 500 newtons. V infinity is 250 divided by 500 into 250. plus m dot E is nothing but exit mass flow rate is air mass flow rate plus the fuel mass flow rate. So if you add up both of them, it would be 100 times 1 plus 0.02. M dot exit is nothing but uh, m dot air times 1 plus m. Okay. And v9 minus v infinity is, since this 250 minus 250, so this part is going to go away. Okay. And if it goes away, this is going to be simply 500 times 250 by 500 times 250, which is going to be 1. Basically what we are telling is we have 100% propulsive efficiency. Okay, interesting scenario, I guess. So now let's try to find out the other way for a moving observer. How will it be? 500 into 250 divided by m dot r is 100 divided by 2 into 1 plus 0.02 times v9 square, which is 250 square, minus 250 square. Okay. So how much is this efficiency coming out to? 1.02 square minus 250 square. So you would be surprised to see the answer. Does anyone have an answer? Anyone quickly find out the answer? So I get something like, which is like 200% efficient. So this is the problem with this way of with this definition of the propulsive efficiency. We all know efficiency cannot go beyond 100%, and that you will not see when you know use this equation, but you would see when you use this equation. So that's why people usually prefer this equation in order to quantify propulsive efficiency. Okay, is that clear?
Yes, sir.
All right, thank you. So, and then next efficiency we have is thermal efficiency. Thermal efficiency, let's you know again we can either write the equation for stationary observer or moving observer. So what we'll do is we'll go forward with stationary. Okay, and for this you can write this as T infinity plus m dot r plus 1 plus f by 2 into v9 minus v infinity square divided by m dot fuel times qr. So m dot fuel times qr is the total energy, that we added. Okay. That's a total power, thermal energy that we rate of thermal energy that we added to the engine. Okay, qr is the heating value of the fuel. So if I substitute all this again, this v9 minus e infinity is going to be 0, so I'm not going to put that. And if I put the remaining terms over here, this is going to be m dot f is going to be, we know it's m dot r into f. So it's something like m dot r into f, which is 0.02 times qr. Qr actually the question didn't give. So what we will do is let's assume qr to be 46,800 kilojoules per kg. So which means we have will be releasing 46,800 kilojoules of energy per kg of fuel that we burn in the combustion chamber. Okay. That is what this QR means. So if I substitute this also over here, you should note that it is in kilojoules, so I will be putting 10 power 3 over here. How much would this be coming? So luckily I have a calculator here with me. If not, you guys need to calculate this and let me know. Probably from next class I will not bring the calculator. So the thermal efficiency that I got is something like this. So which is around 0.134% you can say. Okay. Thank you, Madar. So this is the thermal efficiency that you got, And then finally, if you want to find overall efficiency, how would you find? It's simple. Thermal efficiency times the propulsive efficiency. And the propulsive efficiency, what we are going to use is the first way of calculating it, which is going to be 100%. So this is going to be simply 0.134%. Okay. This is how you calculate the efficiencies, and it's straightforward substitution of equations. Um, and the TSFC, we all know it's m dot f by t. M dot f also we all know it's f into m dot r by t. And f is 0.02 into r is 100 kg per second divided by 500 newtons. So how much is this coming out?
0.004.
Okay, 0.004. Now the units, you should be very careful. It should be kgs per second per newton. So if you remember, this is in kgs per second and this is in newton, so it's kgs per second. So MMR is asking how much is the ideal thermal efficiency for civil aircraft. So currently at the state of our technology is like around people are reaching 40-50 thermal efficiency. That is a 40%, 50% thermal efficiency is what people are reaching. Okay. This is just a sample calculation for us to understand these concepts. That's why don't worry much about the numbers that we get here. But from next week we'll be using real numbers that we see in aircrafts. Okay. So this is all about case 1. Let's then quickly wrap up case 2 also, and then we will plot it. So that would be interesting. So the case 2 is the same thing but with the additional exit velocity, which is 350 meters per second. So u9 is 350 meters per second, or you call it ue also, doesn't matter. And PE or P9 is again 12 kilopascal, so we no need to have any pressure terms. Okay. So the thrust is going to be the same equation, m dot r 1 plus f v9 minus v infinity plus e9 into p9 minus v infinity, where this is going to be 0. Okay. And this is going to be then 100 into 1.02 into 350 minus 250. So this would be the newtons. Similarly, efficiency, we will calculate only for the propulsive efficiency in first manner, like for the stationary observer. We don't do for moving observer. Okay. So it should be. So did anyone is able to calculate the thrust? Thank you, MMR. 10.7 kilonewton. Sorry, I'm calling you MMR. May I know your name? Mihir. Okay, sure. So the propulsive efficiency, how would you calculate? Yeah. So it's just a repetitive task. So m dot r into 1 plus f by 2. It's going to be v9 minus v infinity whole square. Okay. So 10.7 into 10 power 3 into v infinity is, aircraft is still moving at 250 meters per second, so it's 250 divided by 10.7 into 10 power 3 into 250 plus m dot r is 100 into 1.02 divided by 2. v9 is how much is it? v9 350 minus 250 square. Okay, this is the propulsive efficiency. So if someone find it out, let me know. And similarly we can do thermal efficiency also for which the equation is, just for the sake of completion, I'm just writing it so that uh, maybe after this class we don't need to write, we can just directly put in the units. Okay. So it's a good practice when you begin with to write all the equations. So divided by m dot f into, this is going to be 10.7 into 10 power 3 into 250 plus 100 into 1.02 by 2, 350 minus 250 square. So this is nothing but the denominator of propulsive efficiency. Okay, this as an answer, it's 0.83. So around like 83%. Okay, and here it will be m dot f is 100 into f, which is 0.02 into q or 46,800 into 10 power 3. So there will be some propulsive efficiency, sorry, thermal efficiency, and then finally you will have overall efficiency to be propulsive efficiency times thermal efficiency. And then we can also find TSFC, which will be m dot f by t, which is 100 into 0.02 divided by thrust is 10.7 into 10 power 3 kilograms. So do we have numbers for all these three? So thermal efficiency, I have calculated a number. Yeah, so the thermal efficiency comes out around 0.034, so which is around like 3.4% efficiency, and overall it is going to be 0.034 times 0.83. Yes, so this will come out around 2.9%. Okay, you can check this calculations, it's straightforward. And also we also have TSFC. Does anyone have a number for TSFC? All right, I have a number here. You'd be surprised to know that this is your TSFC. So compared to the last case, you would see a much reduction. So last time it was 4 into 10 power minus 3. For example, it's 0.004. Now it's something like 0.186. So let's say if I want to quickly summarize case 1 and case 2. So the thrust, propulsive efficiency, thermal efficiency, overall efficiency, and TSFC if I want to summarize. So thrust was 500 newtons and suddenly it became 10,700 newtons. Okay, and the propulsive efficiency was 100%, and here it was reduced. You can see the UE here is 350 meters per second, and the UE here is 250 meters per second, which is same as flight speed. Okay, and the thermal efficiency was 0.134 percentage. Here it was like 3.4 percentage. And the overall efficiency was also 0.143 percentage, and here it was like 2.9 percentage. You can see the improvement in efficiencies. And also, this is the interesting part, 4 into 10 power minus 3 kgs per second per newton. Here it was point, let's call it 0.19. Okay, 19 into 10 power minus 3 kgs per second per newton. You can see a drastic reduction in fuel consumption. Okay, let's try to reason out why we see, upon increasing the exit velocity, why do we see such variations in these numbers. Okay, so for example, if you go forward and so the second part of the question was is to plot the variation of thrust for different pressures. So what we calculated was the exit pressure of 12 kilopascal is what we calculated. So first let's, with the data point we have, let's try to plot it. Okay. So the thrust would be, let me first plot the thrust. So this is thrust, but what also is given is, let's plot it with respect to, so it was given plotted versus u by uv. So x-axis, let's plot it with u by u. Okay, u is nothing but your aircraft velocity, and ue is nothing but your exit velocity. So let's plot that, u by ue, and the yeah. So when your velocity is, you know, same as aircraft velocity, it's going to be 1. And when your velocity is 350 meters per second, let's say if I want to write u by ue here, it is going to be 1 here. Here it is going to be u is aircraft speed 250 by 350, which comes around 0.71, something around that. Okay, so let's try to plot these two numbers. It's 0.71. The thrust varied from 500 to 10,700. Okay, so it is somewhere 500 will be somewhere over here. Then I think, yeah, some 1000 will be here, and then somewhere on top you will have 1700, for example. Let's say it's just a crude drawing. So you see these two data points, and if you connect, it would look something like this. So I was drawing this as a curved line. The reason is I found out how the variation happened in between these two. Okay, that's why I know this, and I will also tell you how you can also obtain this curve line. Similarly, let's say if I want to plot the propulsive efficiency with u by uv, how it would look is, for one it's 100% efficiency, and for 0.714 it will be little less. So this is like 100% efficiency. So it would look something like this. Okay. And all these are for exit pressure of 12 kilopascal. That is something you need to know. And similarly, you have thermal efficiency, u by uv. So thermal efficiency, what did we saw? We saw a rise in thermal efficiency. So it would look something like this. Okay, this is 1, which is from case 1 to case 2, we saw a rise in thermal efficiency. Okay, this is how thermal efficiency would look. Let's say if I try to plot the overall efficiency, it will look something like this. Okay, so I joined these two lines over here because, you know, thermal efficiency and overall efficiency is same in that region. So okay, this is overall, this is thermal. Okay, and finally, if you look at TSFC, as I said, you will see a stark difference over here. 714, it would be 1. How this would look is, it would look something like this. It would be very much steep towards the 1, basically. Okay, so this is how it would. This is the TSFC variation, how it would do for different pressures. Okay. Now, question to you guys: why do you see such a trend? We will get back to Pratibha's question later, once we discuss these things. Okay. So why do we see this such kind of difference? For example, let's say uh, let's say you talk about thrust. So we see increase in thrust when we increase the exit velocity. So UE increases, which causes the thrust to increase. It's basically coming from the equation. You see that momentum leaving out is high, which means it will produce a lot of thrust. That is the basic simple reason for this. and the propulsive efficiency, you can see it is like 100% over here. The reason is you are not losing any UE here is U9 here, exit velocity of the jet. Okay. UE or U9, both are same. So it is 100% efficiency when you have the vehicle speed and the jet velocity which is leaving is same. What does it really mean? Which means you're not wasting any kinetic energy to your atmosphere. So that's why your propulsive efficiency is 100%. But when you increase the exit velocity, but your aircraft is still at 250 meters per second, what you did is you wasted some portion of the kinetic energy, and that is why you see a decrease in propulsive efficiency, which is around like 0.80, like 83 percentage, right? And the thermal efficiency increases. The reason is, can anyone say why it increases? So basically, you're generating a lot of kinetic energy. So when you increase from U to UE from 250 meters per second to 350 meters per second, you increase the uh, lot of kinetic energy, which is like power input to the system, which you increased, right? And because of that, you see, uh, but during this increase, you didn't change the fuel flow rate, right? Your fuel flow rate F was still fixed to 0.02. We didn't change the F from case 1 to case 2. So for the same fuel flow, same fuel addition, you were able to get a higher increase in the kinetic energy of the system. So that's why you see a thermal efficiency to rise, right? So as QE increases for same F, for same fuel flow rate or same fuel to air ratio, you see the total kinetic energy of the engine increased because UE increased. UE increases, kinetic energy increases, and this causes the thermal efficiency to increase. Okay, so I hope the reasoning you were able to capture. If you know the thermal efficiency, why it increases, you can directly correlate that with TSFC, right? For same F, same fuel flow, I was able to generate a lot of thrust, right? The thrust increased, which causes my TSFC to decrease because thrust is inversely proportional to TSFC. We write m dot f by t. So we have increased the thrust, which reduces the TSFC, which means I can, get a lot of thrust with less amount of fuel wastage. That's why you see decrease in TSFC when we have a higher exit velocity. So is this clear?
Yes, sir.
Okay.
Yes.
Okay, thank you. So actually, what you can do is you can go forward, and what happens here is additionally we have 16 kilopascal pressure. We have increased jet velocity again, and you can find these two cases. Also, you no need to restrict with that. You can try for different pressures, and then you can see what is the pressure effect is. In fact, you can even extrapolate right now, or you can just come up with a logical explanation upon increasing the pressure what would happen. Okay, so I will give you a quick hint. So upon increasing the pressure, what would happen? So when you increase the pressure, you have this pressure thrust, right? So this pressure term will be positive, which means your thrust is positive, so the net thrust is going to be positive. So what happens is, if you can go forward and check this out, what happens is, this is 12 kilopascal, right? So your the additional, the curve will remain same, but the whole curve will start shifting upwards. For example, this would be your 15 kilopascal. For example, let's say this will be like P equal to 15 kilopascal. Basically, you will see upon increasing pressure, your curve will start shifting up. So similarly, you can do for propulsive efficiency, thermal efficiency, and TSFC. You can come up with a logical explanation what would happen when the pressure increases, right? So especially if I want to give you an idea, you have this TSFC here. So as pressure increases, the thrust increases, but the other terms are remain same. What actually happens is this curve starts going down because your TSFC required would be lower and lower because your thrust has increased because of pressure. Okay, so these things you can reason it. I will leave it to you as a homework. So since this is a first class, I think I exceeded the time more than 1 hour I took this. Uh, from next flag, I will try to reduce it to 40 minutes maximum, and the remaining 1 hour. But anyway, I will be available till 9 o'clock. Okay. The remaining 1 hour, you can always ask questions. Okay. Um, yeah. So that is what I wanted to tell you. Uh, yeah. One more important thing is you can continue and finish. You can do this second one also for your understanding how to plot and I mean, you can plot, you can calculate and plot. And now another thing I'm going to give you here is, so are you guys familiar with MATLAB? Uh, so have you guys used any programming languages? So it is not particularly required for this course. You no need to really know the programming language, but it would be a quick if you know MATLAB, or if you can make this, you can write a quick program because it's a very big calculations. It will take um, a lot of time to calculate for each case. So what we usually do is we just write a small program, and we just use that program to calculate for different variables, and we try to plot this basically. So that is how we do. So basically in MATLAB, what I try to do is I try to do the same problem. I have the program here. If you have time, you can run this program. This anyway, I will upload it in a Google Drive, and I will share you the link. So basically the same thing, nothing different. I have taken some inputs over here, and for different pressures and different exit velocities, I was running a loop. These are nothing but equations. So for example, you have thrust equation, which is nothing but m dot r f into ue minus infinity a9 into p9 minus p infinity. So the same thing, and different kinds of propulsive efficiency we discussed in the class. So for all three, I have calculated, but the first efficiency is what we are interested in. And similarly, I have thermal efficiency and also overall efficiency and the TSFC. Okay, so this whole code will actually run in a loop, and it will generate all the solutions the first time. Okay, and then this part over here is same continuation, but it is just to plot it. Okay, so this is just for plotting the all the things like thrust, propulsive efficiency, thermal efficiency, overall efficiency, and TSS, just for plotting. That's why it's very big. This is nothing else. Okay, but the main program is here. It's just I coded the equation. So if you look at it, you can easily understand. So if you know MATLAB and if you are interested in running this program, please feel free to go forward and run it. Uh, uh, so what I would do is, if time permits, I will quickly show you a demonstration also. So let me quickly share the screen from you. Uh, okay. Yeah, I think you all will be able to see my code. So this is the MATLAB program I have. Okay. And what I would do is I will just run this program to show you what happens. So it's the same program, whatever I showed you in the presentation. So basically it creates series of graphs. Okay. So it's easy for you to understand also for quick calculations also. So if you look at the figure 1 over here, this figure, you can see that this is the thrust profile that we plotted. So as one of you calculated, it was around like 10.7, I guess. 10.71 for 0.71 U, and it was like 500 newtons for this. So this is blue line is for pressure 12 kilopascal, Red is 15 kilopascal and yellow is 20 kilopascal. This is the graph. This is how it looks. This is for thrust, and then we have TSFC over here. As I said, this graphs. So this is the increasing. So from blue to red, you have an increase in pressure. So as pressure increases, as I said, the TSFC decreases, and you can reason it for yourself just because thrust is increasing. Okay, so this whole curve actually shifts down. That is what this means. Okay, so this is how the TSFC looks, and thermal efficiency and the overall efficiency looks same. There's not much of a difference, and as pressure increases, this is going to move up simply because thrust increases. Okay, and then we have propulsive efficiency over here. You can see everyone goes to 100%, which is a good metric. If you try to plot a different for a moving observer, this will not stop at 100%. It will go beyond 100%, which is not a right way of using an efficiency. Okay, and as pressure increases, you can see the curve shifting more and more upwards. All right, so I just want to quickly show this so that you can get an idea on why these things are happening, and also you will get a head start in terms of coding. It's actually a good idea, or good you say a skill to have. MATLAB program is simple. It's just you program the equations. Okay, you can have a look at it, but it is not really necessary for the course, or you don't need to really follow this, but it's just an extra add-on that I'm just giving. Okay, so that is all from my side. If you have any questions, you can stay back and ask. I will be available till 9 o'clock in this same place. Okay, but whatever I wanted to teach, I wanted to touch upon, uh, I completed. I will leave the remaining part of this question for you guys to complete. Okay, case 3, 4, and the second part, which I almost already provided you the code. You can go for yourself and see. Okay, so from next class, it will be similar like this. The whole agenda of this problem solving session will be similar. We'll be solving one or maximum two questions, and we will be uh, you know and then I will open for you. I will be available for you to answer your doubts if you have. Okay.
Hello, sir.
Yes, Satish.
Sir, how ramming effect and compressor rotational speed affects the thrust?
Affects the thrust. Okay. So, um, um, so did you? Okay. So this will become more clear as we go forward with the course. For example, in the week 2 and week 3 lectures, you will be you can understand it better. But for the sake of completion, I will give you a quick answer. So when you increase the compressor speed, what happens is you are actually you are increasing the speed of the compressor, which means uh, it actually increases the pressure, basically the pressure ratio across the compressor. So the exit pressure of the compressor will be higher, and we see that most of the times. I say most of the times because you will understand it when you go through week 3. When you increase the pressure ratio, your thrust will increase. So that's why you say that when you increase the basically when you increase the pressure ratio across the compressor, your thrust will increase. Now coming to ramming effect also what it does is ramming effect increases the pressure. Okay. Basically, ramming effect is like suddenly a flow is entering a constricted passage, which causes it to compress by itself. Okay, that's what we call it, ramming effect. And when it compresses, the pressure increases. So by itself, because of the design of the intake, it just compresses, and that's what we call it, ramming. And because of that, the pressure increases, which means the pressure ratio from inlet to the end of the inlet, it will increase, right? And whenever there is a pressure ratio increases, the thrust will increase. So you will better understand it If you don't understand why the pressure ratio increases stress, you I would ask you to go through week 2 and week 3. You will get it more idea about it. So currently you hold on to this explanation. Okay.
Yes, sir. But while studying this thrust equation,
Mm-hmm.
so V infinity will be increase. If V infinity will be increase, so the thrust will be decreases, right?
Yeah, if V infinity increases, provided all the other parameters remain
Constant.
same, thrust will decrease. True.
So in that class, I listened that if V infinity increases, this is because of ramming effect also.
Mm-hmm.
So in that perspective, I asked this question. So
Yeah.
that's why.
So at that time, what happened when the ramming effect increases, the pressure ratio increases. Pressure ratio increases will cause V9 to increase. Okay. So if when V infinity increases, uh, because of ramming effect, V9 also increases at the exit. So when you compare the increase in V9 versus increase in V infinity, for a small increase in V infinity, you can get a very high ramming effect and causing very high V9. So that is why your thrust will increase in that case.
Okay,
Okay,
sir. Thank
so
you.
until unless you do not change any other parameter in this equation, for example, you do not change V9, you do not change anything, any of the thing. If you simply increase the V infinity, thrust will automatically decrease. But what happens is
Okay.
during ramming effect, your V9 also increases. That's why we say actually the thrust increases. Okay.
Okay. Okay. Thank you, sir.
Uh, before we go to Raghavendra, I will quickly address Bharati's question. Sir, in the scramjet engines, exhaust velocity is supersonic or hypersonic at the same time. Inlet velocity would be subsonic or supersonic. So, initial starting state, how engine get that inlet velocity. So, Bharati, you were right. Usually, the scramjet engines it cannot start. So, initially we go to a very high velocity by using a solid rocket motor. For example, in most of the missiles, Agni missiles or you know other missiles, we initially have a solid rocket, solid boosters, and that will reach a very high supersonic velocity. And once it reaches supersonic, the scramjet kickstarts. That is how it go that way. But I heard that about that engine has no moving part. So as a scramjet engine, it doesn't have any moving part. So until it reaches the supersonic speed, it has to, by any means, it has to reach the supersonic speed. It can either be a turbojet or you can use a solid rocket booster. Solid rocket booster also doesn't have a moving part. It's just when you ignite it, the propellant just burns and then it goes to a very high velocity. Okay, so it is true that scramjet doesn't have any moving parts, and uh, purely because of the ramming effect and increase, the pressure will start increasing in the region, ramming region or compressor region, where ideally we do not have a compressor, but air gets compressed, and then it goes through a you know combustion chamber, and then it gets out of the nozzle basically. So the only these three things are there basically. That's the concept. Okay. Yeah, I think Mukti Raja is trying to answer Bharati's question. Okay. Right. I hope that answers Bharati's questions. And Raghavendra, do you have a question? Please feel free to unmute yourself. Raghavendra Kadaki. I think you are still muted.
Hello, am I audible?
Yeah, yeah, yes, Raghavendra. Please go ahead.
Hi Ganesh, good evening.
Good evening.
So, if you go to case number 3,
Mm-hmm.
the exit pressure is around 15 kilopascal, right?
16
So,
kilopascal. Yeah.
okay, so for that case, what is the area of engine that we should consider?
True. So actually, that is also not given for this case. So what you can use is you can assume that to be 1 meter square or so. So something like that you can
Okay,
assume. For this question, you
and,
can assume that. So that's what I did
and
for my. So yeah, that's what I did for over here. Okay. Yeah, you can assume that. I mean, it's not given in the question. So yeah.
And second thing is, why don't we consider the momentum drag or skin friction drag while calculating the thrust?
So the reason is this thrust doesn't have the, yeah, actually it's a good point. It's called uninstalled thrust. So we see it as a as an engine. What is the amount of thrust it is producing is what we are looking at. We are actually characterizing an engine. We are not really uh, trying to we are not actually including the drag which comes because of engine. Okay, with that you do it when you analyze the aircraft as a whole. So the drag because of the engine, it gets added to the, when you do a momentum balance on the aircraft, which I think you might have also studied in the first week of the course. Uh, the thrust is equal to drag that you do, right? So that you add it as a part of an aircraft. You do not add it as a engine. So this is just a engine. How much thrust it can produce because of all this uh, process that it goes through: compression, combustion, expansion. All this process that it goes through. What is the ultimate thrust you are getting out of it is what we are interested in. So in that scenario, you don't really account for drag. You don't account for drag in this case.
Yeah, understood. Thank you.
All right. Any other questions you guys have? I think Bharati, I think your question, I think uh, understood the reason. I think your question has been addressed. If you still have any question, you can unmute yourself. Um,
Sir, I had one doubt for the mass flow rate.
oh yeah, sure.
Sir, regarding mass flow rate, sir, the value changes with the change in altitude, right?
Correct.
Correct.
Yeah.
Yeah. Sir, then in that case, sir, means we have to include the mass of the air.
Include where?
Sir, it is like kg per second.
E- Yeah, so actually I couldn't understand your question properly. So as altitude increases, the mass flow rate changes. That is true. So what do you want to include?
Sir, no, sir. Actually, that only I had doubt. Means for calculation stuff, it will not be constant, one value. So all that will be mentioned.
No, I mean here we are actually calculating for a constant altitude, right? At that altitude, whatever the mass flow rate we are taking in.
So that we are taking it.
Right?
Okay, sir.
But when the flight is taking off, as you said, the mass flow rate will be continuously, changing as it going. Is that your question, or
Is that your question
did I
or yes,
misunderstand?
sir.
Okay, okay.
Yeah.
Raghavendra, yes, go ahead.
So I think the last question about mass flow rate.
Mm-hmm.
So mass flow rate at the inlet, which is for air, is rho into A into V. Okay, A
Correct.
infinity, V infinity,
Right.
and rho infinity is calculated from pressure and temperature,
Correct.
P upon RT.
Correct.
So use that logic to calculate the mass flow rate at given altitude.
Yeah. Yeah. That is a good ad, good way of calculating. Only thing is we need to know A infinity. Yeah. Once you know A infinity, you can calculate. Because so that answers Mihir's question also. So for a given altitude, uh, we know P infinity and T infinity. That is not going to change. From there, you can find rho infinity, and you know flight goes at V infinity. And if you know the passage A infinity which air is getting in, then from there you can find the mass flow. That is how we actually calculate mass flow rate. But most of the questions that we have here, we usually provide the mass flow rate. Especially, we will touch this topic again next week because I have an interesting problem for next week, which is about inlet design. Okay, so There you will know more about the m dot air which is entering. So how are we calculating? All right. So any other questions? So Pratibha is, I thought I this is Pratibha's question. Sir, I have opted for Introduction to Aerospace Engineering Flight Certification. Looks like this is not related to syllabus. Could you please clarify my confusion? Um, Pratibha, I'm not sure about this flight certification courses. Um, uh, so as a aerospace engineering student, I think it's good to study these concepts. That's what I would say. But I'm not aware of this flight certification, so I'm not really a qualified person to answer this. Is this a NPTEL course or something? Introduction to Aerospace Engineering Flight Certification. Uh, Pratibha, you are muted. Yeah, probably she's typing maybe. We'll quickly uh, visit. We'll quickly ask Bharti. Bharti, you raised your hand. Do you have a question? No problem, Pratibha. You can type. Any other questions? Do you have any comments on the pace of my the way the pace at which I am going forward? Do you have any comments on that? Do you want me to improve on this? Do you want me to slow down move it faster? Do you have any concerns with the you know course content? You can also share that. Bharati is asking, can you teach about centrifugal compressor? Uh, yeah. So, okay. So, do you have any specific question in centrifugal compressor, Bharati? Just about the compressor. Okay. So, I will give you a quick idea how this works. So usually centrifugal compressor, as the name suggests, so what it does is because of centrifugal action, it you know compresses the fluid basically. So what happens is you will have something like you know centrifugal pumps, right? Centrifugal pumps are centrifugal compressors. So how would I explain this? So what happens is it is not a yeah, as Raja said, it's because of the angular velocity. So and let me try to draw something. So you will have a, you know, chasing something like this, and then so this is how it looks like. So this is this is the central line. This will be some compressor. This will be keep on rotating. Okay, and when the air enters, so you have vanes which guides the air towards the center of the, it would look something like this. I think my drawing is very bad. Maybe I will come up with a picture of this centrifugal compressor again next week. Okay, but think of it like this. um, the air actually enters via axial direction, I mean radial direction, and then it gets compressed and it goes in a axial direction. That is how it goes. Okay, so because of the angular motion of the air, it I mean you have a stator and rotor plates there also. Because of that, it, or you can say rotor and the casing, because of that it air gets compressed, and then same as centrifugal pumps. What I would do is I will come up with a better drawing next week, and then we will revisit this question. Okay, maybe I will show you a image or something to better understand this. We, and also Mihir is asking, can you give some information on software like gas turbine MPSs? So gas turbine MPSs are like engine design softwares, as you already know, but these are commercial softwares, and gas turb will give you like a 15-day trial or something, and PSS might give you like 1 month trial or something like this. uh, you can use this softwares, but it is not necessary for this course, because whatever this software does, or the basic calculation this software does is what we already do in this course. Okay, you can even write the programs like this, and these are the simple programs which is also there in the gas turbine and PSS softwares. Okay, you can also write simple programs of yourself, and in designing this. Yeah, but GasTab is a good software in which you can actually design new creative engines there. I'm not sure about the NPSs, uh, but yeah, if you get a license, you can use it, but it has only 15-day trial. It's a problem. And Koti Raja is asking, I'm interested to learn about different types of flight structure according to specific engine. Can you suggest any link to pay prefer? So, what do you mean by flight structure, Puthiraja? Different types of flight structure means?
So, like we are infusing some in a hypersonic engine, mean we will infuse some blend structure in that frontal area, sir.
Right, right,
So
right,
each
right.
and every different flights has some different structures.
Okay.
So if you prepare any links, mean I can able to learn about it. So I'm
So
asking this
one
question.
thing is, did you try checking the aircraft engine, book that we refer in this course? So one is this book, uh, Mattingly. I have it over here. Jack Mattingly, Elements of Propulsion of Gas Turbine and Rockets. but I'm not sure whatever you're looking for will be here. Let me quickly look at it. Actually, you can check AIAA education series. Maybe I will type here
Okay,
AIAA
sir. You can, sir.
education series. Okay. Uh, this AIAA is actually a big, a community where they also have a lot of books especially related to aircrafts. Okay, so this book is one of their books. So AIAA education series. In this, you might find multiple books which you are actually looking for, flight structure. So you can look at the contents of those books. Okay, you can find a lot of books from them. Okay, there will be flight structure design, flight aircraft design. This is a aircraft engine design. That is, aircraft design is also separate is there. So probably whatever you're asking for will come in that book. Okay. So I would recommend you to visit this AIAA education series. There will be a website and you can see what are the books they have. If you want, you can buy, or different ways of downloading it. So you can try that. Okay.
Okay, sir. Thank you, sir.
All right. And we have Umar is asking ANSYS software. No, actually, ANSYS software will not be useful for our course, or at least for engine design. As engine design as a whole, it may not be useful, and it won't be useful for our case at least, because here we are modeling each and every component as a system. So ANSYS, I don't think ANSYS has that. So instead, I think you should go forward with CASTER or NPSS. I think that is your question. Is that your question, or do you want to ask something else? Okay, all right, clear. Clear. Thank you. No problem. All right. I will address, the centrifugal compressor in the coming week with you know, some better visuals, just for my reminder. Okay. And also, please attend, this. What do you call, the problem solving sessions. It will be beneficial for you. You will be you can directly interact with me, solve your doubts, and also sometimes uh, you know professor might join. So that's what Professor Chetan Mistry told. So probably he might join in one of the courses. And if you have any questions for him also, I can pass it to him. And if you want him to join for some one interactive session, I can request him. Those things are possible. So Mihir is asking, when is the next session? So the session is going to be on every Saturday from 7 to 9. So there is no change in that. Okay. So till the end of this course, till the end of 12th week, uh, it's going to be every Saturday 7 to 9, same time. Okay. And probably you will be receiving uh, reminder emails also for your registered email ID. And also I will soon share this recording plus the link of this drive folder, so that you can always revisit and you can go through it if you want. Okay. All right. So before next week, so we need to complete the assignment. Yeah. So actually, whatever I give here is just for your sake of understanding. Um, these things, it's not necessary for you to complete. But if you find time, if you find it interesting, you are free to go ahead and complete. But important thing is the assignment you have in your NPTEL website, that you have to complete every week. So probably the first assignment would be sometime, I think uh, probably next week or next to next week would be the deadline for first assignment. So I think week one assignment is still open. You can go ahead and submit it. Week 0 assignment is not really, I think they are taking it into account. So you can go ahead and do the week 1 assignment. All right. All right. Thanks for attending the session. I will be staying here for another 20 minutes or so. You are free to ask. If not, you're free to leave. Thanks for attending. I also hope uh, look forward for the upcoming classes also. Here are calculators allowed in the final exam for complex numbers. So I think there is a on-screen calculator. So probably in computer you might already have a calculator there. Like if, when you write gate, you have a gate calculator right on the screen. Similarly, you will also have a similar calculator for this classes also. But anyway, I will confirm once. But you won't be able to carry a physical calculator. All right. Bharati says, so TVC control important for even roll and change orientation, but aircraft you can also use vertical tail for change here. But Sukhoi Russian aircraft has TVC. What is the purpose of TVC in an aircraft? So it's a very good question. My answer may not be fully right, but I will try to answer. So usually thrust vector control people usually do is to have a vertical takeoff and landing, especially for military aircrafts. So military aircrafts you cannot you know mm, afford a very big what do you call the what is it called aircraft uh, oh my god, I forgot the exact term of this. So you cannot have a lot of so usually if you want to take off an aircraft, there should be a certain distance you need to travel with a high speed, then only you'll be able to take it, right? So you do not have enough runway in most of the situations for military aircraft. So at that time, what people do is they rotate the nozzle to have uh, you know uh, a vertical exhaust so that it can provide you a quicker push up, like a rocket. So that's why they use vertical takeoff. Also, I mean, TVC they use is thrust vector control. They use it for vertical takeoff, and also, yeah, as Mihir is telling, it can also be used as a strategic maneuvers. So, quickly, if you want to turn your aircrafts, if you want to do a quick, you know, stunts with your aircraft in a crude way, TVC will be very helpful. So that's the reason we have TVC. Basically, we just have an exhaust of the nozzle, so flexible, so that you can have all this control. So that is based on my understanding. It could have better explanations also, but I am not well aware of them. I will look into it. For the question. Arnav is asking, sir, a little off-topic question. Being a working professional, I can dedicate to do all the classes and assignments and also the live session, but making time for studying for groups might be difficult. So, will doing the classes and assignments meticulously be enough for final exam, or do we need to dedicate more time to groups? So, Arnav, actually, uh, for this, as far as this course is concerned, uh, following the lectures and doing assignments and also attending this section is enough for your for the completion of this course and also get a certificate. um, But if you get a free time, I would encourage you to read books. So because it gives you a lot of different perspective. That's the reason. But as far as this course is concerned, this is totally fine. This should be enough. You don't need to really look into books. But it's always a good idea if you get a free time. I think you should. I strongly recommend you to look into study. Just you can just read over the chapters because you already studied or whatever we are talking, whatever we are teaching. In the books, it's not going to be nothing different. Nothing is going to be different. Only thing is, additionally, there will be some explanations which we might have missed, or they might be giving additional a different perspective of how you can you know uh, understand a certain same concept. Okay, so mostly I will try to do that. I will try to incorporate all the important missed up explanations so that you don't need to worry about that. But it is also a good idea to read the books whenever you get a free. But for the course, you don't need to worry about it. Okay. This should be sufficient. All right. Thank you, Mihir. I'm also looking forward for future classes also. And also, you guys no need to call me sir. You can call me Ganesh. So it's not a problem. So feel free to call me Ganesh. Um, so how to reduce heat signature from the exhaust? Hmm. Uh, Good question. Signature from exhaust. I So what usually people do is, in terms of turbofan engine, what you have is you also have a cold flow. So if you want to reduce the heat signature, one way is there will be a cold, there will be a core flow and there will be a fan, the cold flow. So two flow streams will be there. This flow over the fan usually will have a lower temperature, and the flow over the core is where we add fuel and combustion happens, and then expands in the turbine and then nozzle. So the temperature of the gases there would be higher. So what people do is they mix this cold flow and the hot flow gases together and expand it further in another nozzle. Okay. During that time, you will reduce heat signature to a certain extent. So that is one way you can reduce the heat signature. I'm not aware of any other technologies that we have. One is you mix it, reduce the temperature, and then give it out. That is the one way. Other way, you try to reduce your exhaust temperature as low as possible. So that is one good thing about the nozzle. So from the nozzle exit, uh, usually in a uh, passenger aircraft or other aircrafts, your nozzle exit temperature might be higher. But in some other in other aircrafts, especially for this stealth technology related aircrafts, what you will have is, so you will have a CD nozzle, and also uh, sometimes see converging nozzle also. When you have that, your temperature of the air at the exit will automatically will be lower. So the heat signature you should worry about is the combustion chamber and the exit of the combustion chamber. That's where the temperature would be higher. The exhaust air will not have that much high temperature, and people usually don't worry about it. Only the combustion chamber temperature will have very high temperature, which gives you the IR signature. Okay, so for example, the combustion chamber temperature or the turbine TT4 turbine inlet temperature would be something like uh, currently at this point of time like 2000 kelvins or so. Okay, but the nozzle exit temperature will be like 900 or 800 kelvins. So the heat signature that you will more prominently observe is in the combustion chamber, that is 2000 kelvin. It emits a lot of radiation compared to the exhaust. So for stealth technology concerned, you people will most probably try to reduce the heat signature in the combustion chamber by cooling, basically based on cooling. Again, in a turbofan engine, they try to use the cold flow to cool that regions so that you can reduce the temperature, reduce the heat signature. That is how people do it. Does that answer your question? All right. Thank you. Again, you no need to call me sir. You can call me Ganesh. Shouldn't be whichever is convenient for you. By any chance, have you attended previous NPTEL courses such as rocket propulsion, where I also hosted the problem solving session? Yeah, IIT Madras. For some reason, I remember seeing you in one of the courses, so that's why I was. No problem. All right. Thanks, Bharati and Pratibha. Thanks for attending. Thanks, Krishna Kumar, for attending. I look forward for your participation in the upcoming classes also.